Hi everyone, welcome to my talk on machine learning and code review. So my name is Philippe. Before starting on the subject, who am I? I'm a security researcher for GoSecure. It's a security company based in Montreal, recently merged acquisition, when I call GoSecure Counterattack. What do I do for the research team? I'm mainly focusing on finding new vulnerability class, developing tool. Some tools are open source. So because I used to be a developer and I really like AppSec, I've started to develop a static analysis tool that I'm going to present also in this talk. So one of them is Find Security Bugs. It's an extension for spot bugs, and its focus it's adding a lot of rule for security to this project that is called Spot Bugs. So this will cover any project that is Java related, Kotlin, Groovy, Scala. There's another project that I've started. It's called Security Code Scan. This won't be mentioned in the talk, but it's covering mostly VB.NET and C#. And because I've done a pen test in the past, I've come to develop multiple burp extensions. So maybe you have used one that I've developed. I'm not an expert in machine learning, but in the past year, I've started using it for a project. So that's what I'm going to present today. So in the first section, I'm going to go through some basic statistical analysis concept. This is going to be mostly theory. I managed to slide in a demo in this part, but this is because I really need to introduce some concept that will be used when I'm going to present the model I'm using for machine learning for this project. I'm going to have a demonstration of the final tool, which is still experimental, but I have a demo of this tool. And I'm going to conclude with a lesson learned from my first experience of building a real project with machine learning. So maybe if you're starting your own project or you have some idea, this is two things that you could consider. So first, this is going to be slightly heavy, so it's going to be a bit of theory, but I have just few concepts to introduce to you to make sure we're all on the same line. So the first element for statistical analysis that most semi-advanced statistical analysis tool will do is symbolic execution. Is contrary to dynamic tool, we don't have access to runtime data when we analyze code. We're purely looking at code. So statically, here I have a pseudocode on the right, and the idea with symbolic execution is we're gonna either try to resolve condition or try to evaluate a state of variable at a specific moment. So, for example, in this pseudocode, we might want to test how can we reach the condition where it's true. So then we transform the condition into an equation and try to solve it. So that's one use case. Not all condition will resolve into an equation, but it can be possible. So then I have a quick example to show you how it works. So really simple example. So I have first a variable that is initialized called A, then a second variable that is initialized named B. And now we have a small operation, multiplication between two variables. Now C, instead of having the actual data at runtime, it's going to contain input 2 multiplied by 2. So we keep only the symbolic form of it. Now in symbolic execution, every time we're going to hit a branch, so a condition, we're going to try to evaluate the different states. So we're going to copy each state. So first we're going to do the path where the condition is true. So we have this state until we reach the end of the method, for example. And now we have the state at the end of the method of each variable. Because there was another path, if the condition was false, where A was added 44, now we have another state that could have been reached. So this is the theory behind a symbolic execution. With a quick example. Symbolic execution is interesting if you want to test how can we reach specific paths. So for example, if you're testing C++ code, a lot of the bugs rely on can we reach this state with this bound +1 or whatever. One other thing that that will affect any language is we're trying to look at the state of variable. So more than just their value, we're going to look for, is it safe or unsafe, or tainted or untainted. So here I have two code examples. So the two things we're going to track with taint analysis is the sources. So are they safe source or tainted if they come from user input? But also we're going to track their transformation. So as we do the symbolic execution, the state might change because there might be a validation with a whitelist. There might be a validation with regex. There might be some encoding with some function appropriate for the context. And we're going to do some validation when we reach some sensible API that does maybe SQL queries, receive as input a template, that sort of API. And we're going to check the state of the sensible parameter. So the left pseudocode, because it's a config, you can assume that it's not something that is going to be controllable from the user perspective, so from an external attacker, for example. While an HTTP parameter likely to be manipulable by a remote user. So, like the symbolic execution, I have a quick step-by-step example of how data analysis works. So, it's going to be similar to the previous code we saw. So first, there's a variable that is initialized with user ID equal. So this is a static string. In find security bugs, this is going to have the state constant, so considered to be safe. Then we have a second variable that is initialized. That's going to be tainted because it's a known API and get parameter. We know it's can be user input. Now we have concatenation. So we have a constant and a taint variable that are combined. This will result into taint values, meaning that once we reach this apply filter, that I think was either a Scala or Groovy API, basically apply a filter in SQL. Now we can check the state of the variable C at this moment and confirm that it's tainted, so we should report this bug as a potential vulnerabilities. Already a demonstration. So quick question. Any people in the audience have already used find security bugs? Yeah, I'm going to zoom in the code. Anybody by raise of hand have used find security bugs? Okay, one person. So the idea why I decided to extend a spot bug, which was called find bugs a few years ago, is spot bugs already has integration into IDE. So by developing rules with this API, then I could develop my taint analysis, and it would integrate with NetBeans, Eclipse, IntelliJ, but also SonarQube and other platforms. So the idea is that a developer would have his project with code. Here I'm using an old WebGoat version. And all it has to do is, now I'm going to zoom. I have the plugin for find bugs, and I can analyze all the project file this way. I'm going to do it slightly quickly. I'm going to scan a specific file just to give you an example. So I'm just triggering analysis for this specific file. Won't take long. So okay, so we can see we have three warnings here. There were multiple calls to execute query, but only three that resolve into a warning. So for each warning, if we click on it, we'll see that in this integration of spot bugs, we'll get a few properties, including the category of the bugs, and we'll also get a small description, brief description of the risk, what not to do, what you should do. So a good indicator on what the solution would be to resolve these vulnerabilities. Now, what's interesting is that in this code, I hope I'm moving not too fast, not all execute query call were flagged as potential vulnerability. And that's important because you don't want to flag every call because the security analyst will just do some triage and at some point will get some fatigue and will miss some actual vulnerability. So those that we can confirm as safe for sure, we should try to eliminate them. This way, it's less work for the developer or security analyst. So here, the reason it didn't trigger vulnerability is, like I described before, this is using a string builder, and all the value combined into the string builder are constant value. So they are safe because we know where they are coming from. In this case, there's no reason to flag this. So even if there's some branch, we can identify that at any point in this method, the string builder will use safe source. The second example, if you look quickly, you might say it's vulnerable, but here there's a small transformation. Because it's an int, there's no injection point that will be useful for an attacker. It will only be able to specify a number, so you won't be able to do a union or any malicious injection with that. So here the code examples are pretty straightforward, but it's doing complete symbolic execution on all the methods. So even if you have assignment, it will track down the variable along the way. Here we have another cases that is supported. Is here we're having an input that will eventually reach the SQL queries. But here we have a transformation. It's not good code. I was just trying to give example along SQL injection example. Obviously, you should prefer prepare statement over manual encoding. But here we're using SAP that will encode the parameters specifically for SQL. So what FindScreenBug will do in this case, it won't mark it as safe, but it will add a tag that it's safe specifically for SQL. This means you cannot use an encoder, SQL encoder, for example, to mitigate against XSS, or vice versa. So those are all three cases that are managed. But there are other cases, just one quickly, that won't be mitigate. Here we have web session, which is a custom class from WebGoat. It's calling get username, and the return value is used in the query. Because FindScreenBug doesn't know about this API, it doesn't know for sure if it's a safe value and if it can be trusted. So for this reason, we're going to raise an error. So this was to give you a quick overview about the tool I'm talking since the beginning, so you have a better idea. And also how data analysis work and what type of cases we try to eliminate. There are still many obstacles. Right now, FindScreenBug does data analysis at method level, so it won't look by default at method calling other methods, so we won't backtrack for variable tracking across multiple methods. And there are many reasons why we cannot, backtracking against multiple methods will miss a few things. First, one of the obstacles to static code analysis is reflection. With frameworks, there's a ton of value that will be pre-filled automatically, either method call or field, just by design of the framework. So those are harder to see from a static analysis perspective because the call is not in the code, it's indirectly. At runtime, the method will be defined. So dependency injection, really similar. So the idea is you're going to have multiple services in your web application, and every of your services will expose an interface instead of the class directly. So anything related to inheritance, it's more level of indirection. Second order vulnerability, this will imply a database or data storage. So think, for example, if you're having an e-commerce website, when you click the submit order button, at this moment, not everything will be done. So it would most likely be pushed to a queue. Then there will be some payment verification. Then some other services will do maybe payment processing. Then maybe the stock will be verified, etc. So not everything is done inline. Because the data is stored in, for example, the database and then read after, it's harder for the tool to know if value read from database is actually user input. And the last two are more related to design. So these are not bad practices, but these are effects that will have effect on a statistical analysis. So encapsulation, anytime you wrap some API, because they are commonly used in your web application, the static analysis tool will have hard time identifying what is actually being used just because you're wrapping the API. And anytime you have custom frameworks, so for the example of WebGoat, where they wrap all the HTTP part in web session classes, utility class, for the static analysis tool, it's all mystery what those API are actually doing. So, but this doesn't mean that these are bad practices. These are actually good practices for other things than security. So I'm not saying don't use framework or don't use dependency injection. But there's two main challenges that result into trying machine learning. I would say the two main were, I know they might don't seem to have a link, but in the end both will motivate the machine learning part that I'm going to talk about. So because we're not doing interprocedural data flow, so interprocedural is just a term to say we're doing data flow across multiple methods. So this, in general, explore the graph and the call to check. This has many. This has some caveat, but some interesting advantage. So one thing I always had in mind is I don't want to eliminate a vulnerability because I'm seeing one path and one case there's a safe source, because I'm not 100% sure that I have all the code. Often you're analyzing just a small component, so you don't know the big picture. Sometimes you'll miss how the framework works. So if there's some dependency injection that you don't see, or some reflection that you don't see, you might not see all the paths. So it's really hard to rely on this to remove cases. But it would be interesting that if we can find a path where it's exploitable, like we can see that a tainted source can reach a valid sync, then it would be interesting to put it in priority to the developer to say, this case, we're pretty sure you should fix it because we have one case where it's exploitable. So we're not necessarily eliminating false positive. That's why I didn't put the effort into it in the early years of find security bugs. Also, proprietary framework and utility, it's an interesting problem because we cannot predict how a company will name their internal classes. But at the same time, if we record enough metadata, not necessarily on the cloud or whatever, but if we record them, we could see potentially patterns. If a specific source is reaching an API and it's always marked as false positive, maybe this API is something safe, maybe a configuration class or something local. So that's the idea. So the perspective I'm trying to do with machine learning is trying more to prioritize rather than eliminate cases, because in security, compared to maybe other field that would use static analysis, in security, one or two vulnerability might be critical and make a big difference, so we don't want to miss any. So the prioritization will help on the efficiency without eliminating and hiding potential vulnerability. So that's the mindset I had when I started the project. So why machine learning? I had always those two idea in mind, trying to do prioritization, and then I listened to a few machine learning talks, and I really saw it seems to connect with my needs. So The general definition of machine learning is we're going to use statistical technique to, based on the data, produce algorithm. So without explicitly program if-else condition with specific value, those algorithms would evolve depending on the data we're inputting to the machine learning algorithm. So that's interesting because I can be really creative at extracting data that might describe the API and the property framework, but it won't be 100% reliable. But because machine learning is flexible and can adapt to the data we're giving as input, this could work. So there are two main classes of machine learning. There are supervised and unsupervised. Supervised rely on human classification. So you need to have a portion of your data set that was previously classified by a human. Unsupervised, it's actually a different objective. We're more trying to cluster data together. So we don't need a human that will classify a specific entry. Instead, it will try to group them. For example, doing image recognition to find similar images. So we're not trying to find specific things in the picture, but we're trying to find similar one. I put an arrow because obviously my use case is supervised classification because I want to classify a few bugs and get the resulting, the remaining bugs prioritized and evolve over time. So we can do a supervised classification if we need to target specific classes. So in the case of my project, is it a false positive or an actual vulnerability? There's also another class that I won't touch here. It's a supervised regression. And this is if we want to calculate a continuous value. So estimate price of housing, for example, time of recovery of an incident, anything that has not a fixed number of classes. So when I say machine learning is producing algorithm, there are multiple types of algorithm that can produce. Naive Bayes, series of conditions, so decision tree. I have an example, won't be too small to read, but basically, when we're going to have new data that is unclassified, we'll start from the top of the tree, and based on each condition, we'll go left or right, and at the end, we'll get our value for the prediction. So that's the type of algorithm it's producing. A neural network is another one. And the idea is that those algorithms are not explicitly programmed. So it will all be based on the data, the training set that we're going to give to those algorithms. Before starting to use machine learning, the first part that you should do is just visualize your data. Because sometimes you might not need machine learning, or you might not need something that advanced. So when I load, this is a Juliet test suite. So these are test cases, vulnerability, but that are made on purpose. It's produced by the NIST. So there are about 30,000 vulnerability that are generated by spot bugs. And those are all the reported vulnerabilities. Those on the left are actual vulnerabilities. Those on the left, right, are all false positive. So just by looking at this simple graph, we can see that for some vulnerabilities, there are actually no false positives. So when we're going to try to enrich our model and add attributes, we should not focus on those, because those, at the moment, for the specific test suite, there are no false positives. So. And one other thing I realized is that most of the vulnerabilities that had false positive in this test suite were injection related. So think of API like SQL injection, XPath, stuff like that. So the value you'll get out of machine learning will be as good as the attribute that you give as input. So garbage in, garbage out. If you just give primitive data that even a human with infinite time wouldn't be able to correlate in anything, it won't work. So what I thought about is we're going to look for an attribute that code reviewer actually look in the code when they do the triage themselves. So if we add a SQL query, what will be the first thing that a developer or a security analyst do is he'll search for any data flow reaching this point and look back, are there any variables that are tainted from this path? But so in an IDE, it would look like this. So the IDE will generate all the path to the specific variable until it reach here. We can see that account number is the dynamic value. And then from this, it could be a method call or a parameter, whatever. Then the developer would take a decision based on this, what he's seeing, what's the context. So the developer will be able to describe what's the business behind this specific API. But here we're going to be able maybe to record the API, for example. So I won't go through all the attributes that we have added to the model, but I'll go to the main one. So the first thing we have added to the model is we're going to record for every bug the source. So if a value is returned and add to a query or part of the sensible parameter, we're going to record the exact signature. So for example, the idea is that we have something like a proprietary encoder that encodes specifically HTML. If there's some pattern where it's commonly used and it end up being marked as false positive, then the machine learning hopefully will be able to detect it. If we have, again, encapsulation on a known API that we won't see, configuration, so anything that will be safe, and the sync will be the API that is triggering the vulnerability, so either SQL or path traversal. Another element is we're going to start to do interprocedural taint analysis, but we're kind of limited. We need to fit those values into either a binary value or a finite number of values. So if we have multiple sources, we cannot have infinite column in our model. So the way we implement it first, in the first iteration, is we're going to first have the state, does one source is safe, does one source is tainted, and if one source is unknown, unknown being any unknown API. There are some property related to localization, so the module name in which the code is located, same thing for file name. So if some component is more critical, there might be more risk in those components. That was the idea. In practice, those didn't work really well. So in order to do those kind of complex query to obtain, does it have at least one taint source, one safe source, we need to model a graph that will cover the complete application. So here in this short code sample, we're having a method load user that will call the API create query. So this is a SQL query. And just for the sample call, we'll have 3 nodes. So we don't want to modelize all the interaction, all the assignment inside the method because this is static. This won't change. But the relation between method will be more volatile. So the idea is we'll track the relation between input and output only, but internal state of method won't be put into detail into the graph. So the first node we're creating is the node 1, which will be the parameter input, and will be linked with the parameter of index 0 of create query. So even though there's still concatenation, it might have some intermediary state, we're only going to track the output, which is the method call that is sensible, and it linked with where it came from. So it could be if we would have a method that return a value or a parameter here in this case. We also need to create another node that will cover the specific API that was vulnerable. So this is needed to cover, to be able to later search on our graph model. So I'm just going to name drop. I was using Neo4j for this project. So we're going to have node for every state, and with this graph, we're going to be able to search for a specific place for each vulnerability to map to the specific variable state. So we're not seeing the complete query here, but it was searching for any value that was added to the add header API. So, but I have a full query next. So with the graph database, you can interact with different API. One of the more standard API is Cypher. So it's kind of interesting the syntax. The first segment, you write it like if it would be ASCII art. So your different node, you're describing them with arrows. And each variable, you can add some filter, like specific matching name stuff. So basically, we're looking for this node will be the element calling the vulnerable sync. So to make sure we're not calling, for example, exec query everywhere it's being called in the application, but this specific occurrence related to the bugs we're looking for. And we're going up to 8 in depth. So this is reasonably far. We're going to match for specific sync and source. So this way, yeah. And the source is for this one to make sure we're looking at the right call. Already the demo. So exit. So one thing I always try to do when I develop tool is look for existing tool, and instead of developing my own UI for classification, I'm reusing SonarQube, which is a tool that basically allows you to classify bugs. So you can review all the reported issue from find security bugs in this UI, and then I can have a state. I can put it as false positive or confirm if it's an actual vulnerability. So what I've previously done is I've scanned WebGoat, all the lessons, so all the exercise. There were about 50 potential vulnerability. I classify 40 something, just enough, but I'm still having some vulnerability that are unclassified. So at the moment, we have a command line interface, but the more stable API is the one using Maven. So this is the WebGoat project. The first step I'm going to do, I'm going to zoom in a moment. The first step is generating the data. So when you're going to interact with different tools, often it's going to be either CSV or CSV++. Usually, different tool will have a different format, but the CSV will have also metadata describing the different attribute, but it will be mostly CSV format. And in this case, so I'm going to just double check if everything is ready. Okay. So on the right, I don't need to zoom. This will be the generated file for the different steps. So the first part, I don't need necessarily to look specifically on the left, but we're going to aggregate first the result from the different reports from spot bugs. There's close to 20 submodules. We're also going to aggregate to each of those bugs the different property that I was talking about, like taint-related stuff, taint, safe, or unknown state related to the graph. So these were generated for every bugs. We also add the different API for sync, source, etc., and other metadata. From Sonar, I'm also poking the state for every vulnerability that was classified or not. So we'll have 3 data sets. So the result is including everything. Label 1 are those that I have confirm or mark as false positive. So this will be our training set. The unlabeled one is those that I have not classified yet. So there's only two commands left. There's the train command. Oops. So this command will generate a model. So this model can be reused, and basically the idea is this will be a naive Bayes algorithm that is used. So once you input into the model a new value, it will classify and tell you a result. Is it a potential vulnerability or is it a false positive? So this is just an intermediary state. Here we have the model that is generated. And finally, what we want to see, we're going to try to predict for the remaining vulnerability some result. So just make sure it works. Okay. I'm going to show you a specific example. So previously I showed you that some cases were already eliminated by the basic find security bugs due to local data analysis. We still had 3 cases that were marked as potential vulnerabilities. So when I classified the potential SQL injection, every time I was seeing session get username, I mark it as false positive because I assume that this variable would have been validated before and it was not user input directly. While, for example, get raw parameter, this is reading directly from HTTP parameter. So every time I was seeing this that led to a SQL query, I would mark this as confirmed. So hopefully, the result of our prediction would put this one higher on the list. And there's another one, which is, again, those code are dummy code. So this sample 6 method is never called. So it has an unknown variable. And yeah, so we don't know where it's coming from. So might be user input, but we don't know for sure. So hopefully this one will also be higher than this one that repeatedly we have put as false positive, at least 2 or 3 times. So it's not a big data set, so the accuracy won't be that high for other bugs, but hopefully for this one, because I know on purpose that in other cases I've put username as false positive. I'm going to search specifically for those 3 cases. So the prediction, it's pretty primitive, the UI. It's going to include the metadata plus link to different resources. So if you want to look at the description of the bug, it's going to link you to the description on the Find Security Bug website. So you get something similar to the IDE, but really, if you need to validate the code, you would need to do it into in an IDE or a Sonar Cube, for example. So here it's going to open, and we get to the bug. One thing I need to precise. So here the probability is the probability of being a good, so being a false positive. I didn't do this interface, so at first I was confused, and I was wondering why it didn't work. So those 2 are less likely to be vulnerable than this one, with at 8% is likely to be a false positive. So, and if we open it, this one is the one where it's using get username. So this source, because we know that in other instances of SQL injection, this API was used as source, then it's less likely than the other to result into an actual vulnerabilities. So the expected use cases or the method to use would be you sort the bugs into the probability, and the lowest percentage would be those that are the more likely to be actual vulnerability and until the end. So if you would have more bugs, then you can just review 10 or 20 and then redo the step I did to retrain and predict again. So maybe there would be some change if, for example, you hit few type of vulnerability that are often false positive, then maybe that retraining the order will be better. So that's the general demo. Back to the slide. So I'll go quickly through the result. This graph, I realized that with the color, it won't be really clear, but anyway. So initially, this was the Juliet test suite. So all the reported vulnerability were expected to be bad because they were reported. But everything on the right is false positive. Now, after the classification, with those attributes that I mentioned, all the dots that you see that are not matching those, so the color doesn't match with the previous graphic. That's the thing. So every blue dot that you see on the right part are going to be false positive, and every red dot on the left will be false positive that are not actually bad, but should have been placed on the other side. So we can see that on large scale, it worked pretty well. The thing with reality, so Juliet is vulnerability with that are kind of fake because they are semi-generated, and it's a large data set that include a lot of false positives, but almost as much actual vulnerabilities. This is the result we got with Spring Framework, and it's a completely different data set in terms of the number of actual vulnerabilities. So it might be encouraging to see up to 95% accuracy, but this is something to be aware, especially if you're buying tools that give you stats about, oh, our machine learning is working so well. The accuracy is based on true positive plus true negative on all other cases. So if I look at the confusion matrix here, I classified about just over 600 bugs, but only 28 of those were actual vulnerabilities. That means a lot of those were false positive, and there's a small percentage that I didn't review. There were maybe 700 total. So the accuracy is only based on those that were correctly classified, but the thing is there's so little actual vulnerability that the percentage climbed really high. So there's two things that we can answer to this. So first, we could take the approach, okay, because in this case, we have so many, actually 0 false negative, false negative. That means that we could, for example, in a CI, alert developer directly, because we're so sure that the bugs that are going to be classified higher than 50% are actual vulnerability, then maybe we could alert them directly to the developer, because developers don't have infinite time to pass for security. So every time they need to spend time on security, it needs to be well worked. Another thing is we can lower the threshold. For example, by default, algorithms are using 50% because they try just to have the maximum accuracy. But if we're able to tolerate some false negative, actually, no, these 22 are the false negative. Here we add 0 false positive. But anyway, so for some vulnerability type, it worked well. Like there were 4 XSS, and it was always finding those. And the thing is, there were different vulnerability classes for almost all of them, so maybe it didn't help. We're still using a tool to find bugs just to feed our model, because that's the main thing we're missing. We're not having large vulnerability that are actual vulnerability. It's easy with Juliet to have 30,000 vulnerability, but these are not real-world vulnerability. So we're continuing to find some vulnerability. So just before the summer, we reported a few vulnerabilities in spring that were done during our triage. And recently we have started to do more proprietary library. And this seems to be cases where we're finding much more vulnerability compared to open source library. So we're going to release an article and maybe next month related to the different RC that we have found. So these are not all the vulnerability. I'm excluding all the medium one and the less interesting one. So lesson learned. If you would have to start a machine learning project, what I would like to tell you is first focus more on the model than the algorithm. So it's easy to just take the data that you have that is probably poor and try to different article to gain 1% or 2% better, but if you have a quality attribute, this is going to do the difference. Always inspect your dataset. It's easy to generate dynamically some value, and you realize that after the time value is missing or it's not as expected. One thing that my colleague has observed is that some machine learning, if you don't specify a value, like it's null, like it doesn't apply, because some algorithms don't support empty values, they'll simply skip the data. So this is pretty bad, and it won't trigger any warning. So try to place a dummy value to say doesn't apply, NA, or whatever. This way you're sure that it won't eliminate your data. Basic stuff, don't mix training set and test set. And these are, do I have still a few minutes? Okay, perfect. So I'll finish the slide. The training set needs to be close to the test set. So one of the main problems we had, if we review few different libraries, often the API used in those libraries won't match others. So it's really hard. We were trying to add more attributes that are more generic, but it's really hard to have a significant one. So that's one of the reasons I've started to pull 120 Spring libraries and focus on those, because my expectation was that at least some components will reuse some of the same code. And at the moment, aggregating a dataset doesn't work as well as expected. So at the moment, the demo I've done, it's experimental. The code is out. It's on GitHub. The graph part was released end of last year, but it's still experimental. I wouldn't use it in production because you can have some good results some week, and the next week you do some classification and it's not working as expected. So the good news is I'm using it in a different way than I expected. So just by scanning massively code, I'm seeing from a statistical perspective. So when I analyze, for example, a decision tree that are generated in machine learning, I'm seeing, for example, bug type that have very high false positive that I didn't expect. So we're going to try to produce some profile that eliminate those, so that people that don't have just short amount of time to do scanning can use those profiles to eliminate some noise. Also, we're seeing some source that are maybe actually an encoding method that we should add in the configuration of find security bugs. So if it's always a false positive when this method is used and it's a public API, why not add it to the find security bugs as an encoder if it applies? Also, sometimes things that always trigger false positive, like I have one case in mind that we're going to remove from find security bugs. There was a XSS vector in a send error in G2E that there was an XSS that applied, but only on vulnerable version of Tomcat. So it made sense 4 years ago when we had the rule to detect potential XSS. But now, if you didn't update Tomcat at this point, you have bigger problem. So I'm done with my presentation on the project. But tomorrow, if you want to have hands-on experience on machine learning, this is going to be an intro level. So if you have no prior knowledge of machine learning, I'm going to use Orange as a tool for the exercise. So Orange, the interesting part is there's a library part, but there's also a GUI part. So we're going to do no programming. So only inserting in the canvas widget, connecting them. We're going to be able to train some algorithm, get some visualization, So if you want some hands-on experience to have an ID, we're going to use two datasets, Titanic dataset, which is a classic one used in machine learning. And the final exercise is with data that I've produced in my project to give you more security perspective. So that's tomorrow. If you're interested in machine learning and maybe try to experiment for project at work or personal. And I'm done. So if you have any question,